Good evening everyone, Assalamu alaikum. I am Saja and today I will be explaining Chapter 2 of Engineering Thermodynamics, focusing on the properties of substances and their pressure, volume and temperature behavior. First, what does matter mean? Matter is an object which has a specific mass and occupies space. So matter is everything around us. Everything around us is matter, even us. So matter is classified into two main things, which are pure substance and mixture. Pure substance means that a matter which has a fixed or constant chemical composition and unique properties or distinct properties. So also pure substances classified into two main things, which are element and compound. What is the difference between element and compound? Element consists of just one type of atom, like oxygen. We have oxygen or nitrogen. Any element from periodic table, it considered as element. So elements made of only one type of atom and cannot be broken down. But compound, it has a mixture of elements or more than one type of elements, like water, H2O, or carbon dioxide, etc. So then if we go to the mixture is made of two or more substances that are not chemically bonded. So they are just physically bonded. They are not chemically bonded. So also we can say that mixture is like when we want to mix water with salt, it's called a mixture, and it's homogeneous mixture. Why? Because the salt dissolves in water, so it doesn't form any layers. We see it, we visualize it as one layer. So mixture classified into two things, homogeneous and heterogeneous. Homogeneous, for example, if we take salt and water or sugar and water. And heterogeneous, an example for it is if we have sand and water. Will it mix? Of course not. Homogeneous mixture is the composition of the constituents is uniformly mixed throughout, like water and salt or water and sugar. But heterogeneous mixture is the mixture that is non-uniform, in which the components separate and composition varies, like sand and water or oil and water. They form two layers. We can visualize it as two layers, two different layers. Going to the examples of what we learned before minutes. Pure gold bar is considered as an element. So its element, Au, gold. So its element. Sugar is considered as a compound, not element or something else. Why? Because sugar is, if we write the formula of sugar, we can figure out that is C6H12O6, which means that it consists of carbon, hydrogen and oxygen. So pure gold is element, sugar is compound, tea, of course, it's a homogeneous mixture. Oil and water is heterogeneous mixture, as we said before. Remember, a pure substance does not have to be of a single chemical element or compound. So we learned that a pure substance classified into element or compound, right? So why it's written that a pure substance does not have to be just single chemical element or compound? So that means that a pure substance is not limited to just be a single element or even a compound. Instead, a homogeneous mixture can also be considered as a pure substance in certain contexts. So So also we can classify a pure substance. We can classify homogeneous mixture as a pure substance. So pure substances include elements like we said, gold, silver, oxygen, nitrogen, any element from the periodic table, or compounds like sugar, water, so or anything made of two atoms. I mean, like water, it's made of hydrogen and oxygen, so it's considered as a compound. Also, homogeneous mixtures can also be a pure substances because it's uniform. It's it's just it's mixed. It's one layer, so it can behave as a pure substance in thermodynamics, like air. Air is a mixture of nitrogen, oxygen, and other gases, but since it has a consistent composition, it is treated as a pure substance. So a mixture of various chemical elements or compounds also qualifies as a pure substance as long as the mixture is homogeneous, like we said. So what's the difference between a pure substance and not a pure substance? A pure substance is, it's like, you have to remember that a pure substance has the same chemical composition. It's the opposite of not pure substance, because not a pure substance is the chemical composition is different. So a pure substance, like air, is a mixture of several gases, has a uniform chemical composition. A mixture of two or more phases, like liquid, gas, solid, etc., of a pure substance is still pure substance as long as the chemical composition, it should be constant. It should be the same. So chemical composition of all phases is the same. A mixture of ice and liquid water, because phases have the same chemical composition, not a pure substance. A mixture of oil and water, since oil is not soluble in water, because oil cannot be dissolved in water. It will collect on top of the water, forming two chemically dissimilar regions. So it will be like two layers, like we said before. A mixture of liquid air and gaseous air, since the composition of liquid air is different from the composition of gaseous air, and thus the mixture is no longer chemically homogeneous. This is due to different components in air condensing at different temperatures at a specified pressure. Going to phases of a pure substance. Since we were kids, since we were in schools, we learned that there are three phases, which are solid, gas, and liquid. So a pure substance may exist in different phases, like solid, liquid, and gas, which are dictated by the microscopic structure. So pure substance exists in three phases, which are solid, liquid, and gas. There are three pictures representing the three phases of the matter or of a pure substance. So the first one absolutely will be a solid. Why? Because they are tightly fixed together. So why they are tightly fixed together? Because they have the strongest intermolecular bonds. So they are tightly backed together in a fixed structure. So, and about their movement, they will not move, but they will vibrate. Why? Because they have a very low energy, so they cannot move like liquid or gas. They are just fixed together, but they will vibrate. So here is the solid phase. Second thing is the liquid phase. In liquid phase, the molecules will start to move. They will move a little bit faster than solid. They are between solid and gas. So molecules are close together but not fixed. So they are close together but they are not fixed like solid phase. So they will move faster than the solid. So they can flow and move around each other because they have higher energy than the solid. So, and about their intermolecular bonds, they have medium, the the strength of the intermolecular bonds are between solid and gas. So their bonds are weaker than solids but still hold molecules together. So then if we talk about gas phase, we can see that they will move very faster, they will move randomly because they have a very large energy, they have very high energy. So the energy level will be the highest in gas, and the energy level will be in solids will be the lowest, and in gas phase they will be it will be the lowest, the highest energy level because they are moving fastly and randomly. So about their intermolecular bonds, they have the weakest bonds. That's why they are not fixed. They are not fixed like solid or liquid. They are not tightly packed. So that's it. And an example of gases like air or steam or any other gases like nitrogen gas or gases or other gases. So this is solid, liquid, and gas. Solid three-dimensional pattern, fixed position, continually oscillate about their equilibrium position. Molecules have low energy level. Intermolecular bonds are strongest. In liquid, molecules are not at fixed positions. Molecules have high energy level, and in gas, molecules are far apart from each other. Molecules move randomly and continually collide with each other and the walls of the container. Molecules have the highest energy level. That's why they are randomly moving. So about their bonds, intermolecular bonds are the weakest. That's why they are not in a fixed position. See the movement of the phases of the molecules in different phases. In solid they are vibrating. In liquid they are starting to move. But in gases they collide with each other and with the walls of the container. Also they are moving randomly and very fast. Phase change process, liquid to vapor. Actually, if we consider the liquid as water, so we have 5 states here. In the first state, the water is under 1 atm and at 20 degrees Celsius. So we will call it compressed liquid in the first state, and the pressure we will keep it constant till the end of the process. So then in the second state we will increase the temperature. So the temperature will be changed into 100 degrees Celsius, and the pressure of course is fixed. So but we will change the name of the state. So we will call the liquid in this state, in the second state, as a saturated liquid. So it's saturated liquid. Why we will call it saturated liquid? Because the water has reached its boiling point. It reached 100 degrees Celsius, so it's ready to start vaporizing. That's why it's called saturated liquid. Then in the third state, the liquid will vaporizes. So as more heat is transferred, part of the saturated liquid vaporizes. So here the liquid will be called as saturated liquid vapor mixture. So we will have water and vapor. we'll have liquid and vapor. That's why it's called saturated liquid vapor mixture. And in the fourth state it will be called saturated vapor because it transferred to be vapor. So we will not see liquid anymore, it's all vapor. At 180 atm pressure, the temperature remains constant at 1 degree Celsius until the last drop of liquid is vaporizes. So in the first state it's saturated vapor, in the second state it's saturated liquid, and in between of them it's saturated liquid vapor mixture. I'm saying it again because to be easy to remember. So in the fifth state, as more heat is transferred, the temperature of the vapor starts to rise. So here we will increase the temperature till it becomes 300 degrees Celsius. So the pressure will be constant as we said before. So then the liquid will be called, not the liquid, the vapor will be called superheated vapor. As more heat is transferred, the temperature of the vapor starts to rise. Then we have this graph. It shows that in the first state the liquid will be at 20 degrees Celsius, then it will be at 100 degrees Celsius. Here is liquid, here is compressed liquid, here is saturated liquid, then liquid vapor, saturated liquid vapor mixture. So and the temperature is 100 degrees Celsius. In the fourth state the temperature is constant, but the phase has changed, so it will not be liquid anymore, it's vapor, it's saturated vapor. And in the fifth state it will be superheated vapor, and the temperature of course is constant, but see, the temperature has been raised, so it's 300 degrees Celsius, but the pressure is constant from the beginning till the end. It's constant, the pressure, but the temperature is changing. But in the three states, in the second and third and fourth state, it's 100 degrees Celsius. You should remember it. And here, that's it. And here is another diagram or another graph for what we learned. I'll try to break this graph down. So from the first state to the second state, we will call it as sensible heating because the temperature will be increased from 20 degrees Celsius to 100 degrees Celsius. So we added heat, and the temperature has been increased from 20 degrees Celsius till 100 degrees Celsius. Compressed, it will be called compressed liquid, then saturated liquid. So it's sensible heating. And from the second state till the fourth state will be called latent heat or vaporization. So here saturated liquid will turn into liquid vapor mixture, then liquid vapor mixture will be saturated vapor, it will turn into saturated vapor. So this will be called as latent heat of vaporization. From the fourth state to the fifth state, we will call it heat of superheating. We superheated the state. So the temperature was 100 degrees Celsius and it became 300 degrees Celsius. So that's why it's superheated. We superheated the state. Saturation temperature and saturation pressure. During a phase change process, pressure and temperature are dependent properties. If the value for one of them is known, the other takes a certain value. What does that mean? That means that if you know one of them, the other one will be constant. So the pressure and temperature are linked together. if you know one of them, you can know the other one. So then we will go to the concept of saturation temperature. At a given pressure, the temperature at which a pure substance change phase is called the saturation temperature, or Tsat. So, for example, at 1 atm, water boils at 100 degrees Celsius, or it's ready to start boiling. So the Tsat here will be equals to 100 degrees Celsius. Then, at a given temperature, the pressure at which a pure substance change phase is called the saturation pressure, Psat. So if they give us the temperature, the pressure, the changing in phase at that pressure will be called saturation pressure. Or meaning to say that, for example, if we have at maybe I will say that at 100 degrees Celsius, the pressure needed to boil water is 1 atm, right? So here the Psat will be equals to 1 atm. That's it.